Hello, I'm Mitchell Sandoe, Product Manager for ScanImage at MBF Bioscience. At some point, you will have assembled a MINI2P, and at some point after that, you will want to image with it. Here, we'll go over how to set up and control the MINI2P in ScanImage. So the MINI2P and optical table will have several devices that require various signals to control. How do we get them? We calculate them with ScanImage and provide them with the VDAC. The VDAC is a PCI Express card with Xilinx Kintex UltraScale FPGA at its heart for fast data collection and processing. It comes with a single breakout box with 12 analog outputs, 12 analog inputs, 16 digital input or output ports, 8 digital input ports, and 8 digital output ports. It has four high-speed analog inputs for receiving amplified PMT signals with sampling rates up to 125 MHz. And possibly less relevant here, but worth noting, is a clock input port which can be used to synchronize sampling rate to an external clock. This is useful for some premium features like acquisition gating for low repetition rate lasers and time-correlated single photon counting. For photon counting and possibly fluorescence lifetime imaging data collection, we have a high-speed version of the VDAC that can collect at sample rates up to 2.7 GHz. A standard speed VDAC can be upgraded to this high-speed VDAC. For more specs, you can visit our product page on our website, or you can scan the QR code here to go straight to the datasheet. We say that the VDAC is an all-in-one solution for your microscope, not only because it is a single DAC card and single breakout box solution with all the I/O that you may need, but also because we develop ScanImage such that the VDAC can support all microscope configurations that ScanImage is capable of supporting. And ScanImage is capable of supporting a wide variety of hardware combinations. We provide generic and product-specific implementations for scanning, supporting resonance scanners, Gavo scanners, and also polygonal scanners. But most importantly here, the Miracle MEMS scanners. For beam power control, you can control Pockels cells, motorized half-wave plates, and as described in the MINI2P cell paper, the AOM that is built into the Toptica Femtofiber Ultra laser. For FastC, we support piezo objective stages, piezo-actuated remote focusing mirrors, and here we support the electrically tunable lenses like the Micro T lens. We also support several light detection devices so long as it outputs a signal capable of driving a 50 ohm load at 0.5 to 2 volts peak to peak. ScanImage can automatically turn these PMTs on and off with the start and end of each acquisition. We support any shutters which can be controlled via a digital signal. We also support a variety of motorized stages like the Thorlabs Kinesis stages, Sutter MP285, some PI stages, and in particular, we like Zaber stages for their software implementation, which provides a very stable interface. Using these devices, ScanImage then can, of course, coordinate planar and stack acquisitions and organize the PMT data to form images. So without further ado, let's see how one goes about configuring and using ScanImage. So, the first thing that we're going to want to do is to download and install ScanImage and the GitHub repository for the MINI2P toolbox. Let's see. For the MBF Download Center, after purchasing a ScanImage license, you'll be provided a username and password which you can use to log in. I'll go ahead and use mine here. And then from the Downloads tab, you can download the software that is available to you. We have an exe and a zip version. The exe, you can just run it and it will automatically put the source code into a program files Vidrio folder, and then also set the MATLAB path so that MATLAB will run the version of ScanImage that you just installed. Here, I'll go ahead and use the manual version and just kind of show you essentially how you would do that with the manual version. So I've already downloaded that, and in order to license this, later you will need to come to My Subscriptions and then find your activation key to use with your system. License keys are one per computer, so make sure it's the computer that you'll eventually be running experiments on. So if you want to download the GitHub repository for the MINI2P toolbox, you can either come to this button code here and download the zip, or you can download a release version here. I've already downloaded the zip of the repository, and we'll be using that. So you can copy the zip file of the ScanImage source code, and then we can go to C, Program Files, Vidrio, and here you see I've already copied it in here and then extracted it. And in order to put this source code on the MATLAB path, from the Home tab, go to Set Path, and you can go to Add Folder and navigate to that very same directory where ScanImage was placed, and then just select Folder, and now this is the code that will run when you execute ScanImage to check. You can use the switch function, and it should read the address where you placed the source code. And so now we can launch ScanImage, or at least get to the launch screen. And before that, it will ask you for a machine data file. And we're going to get this machine data file from the MINI2P repository. So here it is. I had already extracted it. I left it in my downloads folder, but you'll probably want it in a place where it won't ever be deleted. So make sure to copy it into documents or some other folder. And then the address for where the machine data file will be is within the software folder under SI settings. Today I'll use the machine data file with the 2000 Hz for the MINI2PL device. And let's go ahead and take a look at some of the configuration settings that are stored within this machine data file. Now there's a few quirks about this machine data file. I think I've already modified this just slightly. I removed a stage. There's a legacy stage. If you don't have the PI, I think it was a C884 or something, then you can just remove it. You would do that by, let's see, here's an example of adding a device, just as an example here. There was a legacy stage, say it was a PI E861. So if you had a stage that you were not going to use, or if it was the wrong stage and not one that should be used with this driver, then you can click this remove button. That will remove it. And yeah, that's it for that little detour. So actually first let's look at the ScanImage tab and we can talk about these components. So each one of these buttons are assigned to a component, and a component is something that you can essentially think of as a software layer where we take the devices that we've defined here and define a subset of those devices that we can use in a meaningful way, like for imaging or for photostimulation, SI motors. If you configured a stage, maybe you have two stages, one for XY and another for Z. You can select from the available stages to set the XY and Z axes. The MINI2P imaging system that we have here, this MINI2P_001, is a collection of devices. We defined a DAC board where we're going to receive the PMT signals. You can invert the PMT polarity here to make sure that dark regions correspond to the black pixels in the image and the bright regions correspond to the white pixels. And then you can also define a device as your resonance scanner. In this case, we're actually going to use the x-axis of the MEM scanner in a sort of pseudo resonance scanning sort of way so that we can leverage our resonance scanning pipeline to image at faster frame rates. And then we'll also use a Galvo device for controlling the MEM's y-axis. We have a series of shutters. Shutters in ScanImage are kind of they're just an easy way to implement a TTL signal. So some of these, like the LED, probably isn't actually a shutter. Maybe it's going to a LED controller. But yeah, bear in mind you can use some of the devices in ways that maybe we didn't anticipate, so long as it fits what you were trying to do in your experiments. That's fine. So there's also a beams device here and the micro T lens. So these are all devices that we had previously defined. Let's go look at where we can configure those. So yeah, back to the so this is what we had assigned to that resonance scanner axis, and you can see that the zoom control and sync channels. Sonny boy, Sonny, calm down. You can see that zoom channels were filled out here. Zoom channel and sync channel, all the ports that need to be defined for a device will be available in each of these pages, as well as configuration settings like scaling voltage to set the relation between what voltage you're sending and the optical degrees range if it's a scanner, or scaling for power for a beam modulator device, and yeah, many settings like this. For me, there are a few settings here that I will change. For you, you should probably leave most of these settings the way they are, but for me, I'm actually scanning on two actual Galvo mirrors that I don't want to run too quickly, so I'm going to reduce this nominal frequency to 800 Hertz for me, and then for the sync phase, there is 100 degrees of sync offset that has been set here by default with this machine data file. The sync phase is a parameter that may need to change. This sync pulse occurs once per left and right sweep of the mirror. If there is some lag between the commanded and actual mirror positions, one can adjust the phase of when this pulse occurs. There is a similar function in the configuration window, which we'll talk about later. But for me, this scan phase is a bit much. I think maybe 50 degrees is appropriate. And that should do it. Just to show you, we have a shutter for the laser here on this channel. Oh, and if you were wanting to know where everything was hooked up, then you can click this button here in the widget bar. This breakout button will summon this breakout window, and it has all of the ports labeled so that you'll know where to connect each of the B and C connectors. Coming back to our laser shutter, you can see we have 4 shutters configured here. And like I said, you could configure the port. You can also configure how long it takes to open the shutter so that ScanImage makes sure to wait this period of time when you first start an acquisition to allow it to open before actually starting to acquire. And you can define it to be either an excitation or detection path shutter, depending on whether it's just in front of a laser. So this would be a laser shutter, so this would be an excitation shutter. And then for the PMT, this would actually be a detection type shutter. The distinction I don't think is used very much in the back end in ScanImage, so it maybe does not matter so much at the moment. Right now, I think this is used in the context of photo stimulation. So maybe you don't need to worry about this so much. Okay, so for the beam modulator, you again assign a channel. You can assign a minimum and maximum voltage to cover the range that you can use to modulate the power. Here we've already got a measurement of what power you might expect to see at the sample. You might calibrate yourself at one point. If you wanted to limit the beam power to never go above a certain percentage of power, you could set a value here, and then this is for calibration, but since we don't have a feedback channel assigned, and also since it appears that this is the machine data file, all the information that we input into here will be saved into this actual M file. And so for the feedback and whether or not the feedback is using rejected light or a shutter needs to be opened during the calibration, the information that would have been collected for such a calibration is already filled out for you in here. Here we go, power fraction to modulation voltage lookup table. So this may already work well for you. For the fast C, you again assign a channel, and we have the scaling factor for the voltage, and a upper and bottom travel range, and a park position. Some people may decide to put the park position right in the middle of the travel range, and that's maybe sometimes a good thing to do if you want to have space above and below where you're starting out when you're previewing. And then we use just a Galvo device for the y-axis of the MEMS, so that we can scan along Y. All this does is it generates an analog signal corresponding to the positions that we want it to be steered to during the raster scan. And so I guess we've kind of gone over all of these settings. We can go ahead and launch. Okay. So now we've got ScanImage up and running. We don't need the resource configuration anymore. Let's go ahead and do a planar acquisition. So when you launch for the first time, this scan phase will be set to 0. So this is a scan phase that instead of this scan phase that you define from here is actually something you output from the VDAC. And this is here normally for a resonance scanner, which you can't control the phase of a normal resonance scanner, but you can, if there is some offset between where we expect the resonant scanner's mirror angle to be and where it actually is, see, we would expect the rise of this period trigger to be at the very local minima of the angular scan angle waveform, but for a normal resonance scanner, sometimes there is some lead or lag, and so you can compensate for it by adding some time in this scan phase box here. So if when you focus you find that, that's right. So I had already acquired here before, and each time that you acquire and you adjust the scan phase, it will, for the amplitude that you're scanning at, it will save the scan phase to a lookup table. So if you're at zoom is equal to 1, and you change zoom, and then you come back to zoom is equal to 1 again, if there were different scan phases that were appropriate for different zooms, then it's going to apply the appropriate scan phase. But normally there would be you would start with 0 microseconds scan phase offset. This is a misalignment of the even and odd lines of the image, and you can click auto adjust, and that will use the image to determine what the offset in microseconds is between the even and odd lines, and you could use that, or you can manually adjust the scan phase yourself. And another important component of the first planar scan is the contrast. So if you right click in the image, you'll have this histogram option and also auto scale contrast. If I auto scale the contrast now, while we're looking at the histogram, we'll see that this gray region has expanded to capture most of the pixel values, and You can also adjust the contrast by sliding this grayed portion of the histogram around. If you click close to the border, then you can drag just one border. And these controls are also available from the image controls window. So many ways to control contrast. There's also frame averaging. So if you're getting a bit of random noise in your images, you can increase the frame rolling average factor for display. This will maybe give you a bit of lag in the fluorescence signal as displayed here, just since we're doing a moving average. But for display, it's maybe preferable. As you'll see in the beam controls, I actually have not set a power, but that's because we don't have a Pockels cell. But for this 920 nanometer AOM incorporated into the Toptica laser, you would be able to set the acquisition power via this slider, or you can enter in a amount of laser power in percent, and that would apply that power in the frame. There's also power boxes, which are a good feature if you want to isolate power to certain parts of the field of view. This power here is the same as this power here, but it's only going to apply inside of this box. So this is, maybe I want 10% of the laser power inside of here, and then everywhere else it would be 6%, whatever is left here. And you can have multiple power boxes. So maybe 10% here and 15% over here. I think this is a noteworthy thing to show. And if you want to actually apply them, you need to click Enable Power Box. All right. If you have a stage, then while acquiring, you can move this stage. All the units displayed here are in microns. If you click in the display here, then it'll allow you to set a new position via entering text. So maybe I want to move 30 microns with this stage. You could enter 30 microns in for the Z position or not. Maybe you want to move Y 30 microns. And this should reflect the position in these sample coordinates. So there are sample coordinates and raw motor coordinates. Raw motor coordinates should correspond to what the controller says the position is, and the sample coordinates can be zeroed at any time whenever you're at a location of interest, where this should be the center of the sample coordinate system. You can zero at any time and then measure relative to that. If you want to move your FastC location, you can change the Z using your micro T lens like this. And you can see your ranges from +10 to +10 to minus 250. One thing that sometimes can trip people up is this display of the coordinate system here. So we have sample position in Z on the right and the FastC range on the left. So we are at position -40 with our micro T lens, This is reflected on these left axes here, but as our sample position with the stage is in combination with the micro T lens, our resultant sample position is 10. Also worth noting is, rather than adjusting the micro T lens position via these up and down arrows or by editing this editable text for the target position, you can actually, if you hover your mouse over this graph, and if we set an appropriate increment from here, maybe you want to move 1 micron at a time, you can just scroll with your mouse wheel to change the fast C position or your micro T lens focal point while you're focusing, and you can find regions of the, or slices of the sample that you would like to image at. But let's move on to the channels window. Right now, the channels window is only showing a single channel for save and display. Normally you have 4 channels, one for each of the physical channels. I actually narrowed it down to just a single channel with the physical channel that's actually receiving the signal. But normally they would be assigned like so, with AI0 to channel 1 and AI1 to channel 2 and so forth until channel 4. With premium ScanImage, you can have as many virtual channels as you want, and you can do different sorts of things that we can go over at another time if you'd like. But the important thing about the channels window is this display and saving ability. So if we know that our signal is coming in on high-speed analog input 1, and we know that that's assigned to channel 2, then we would do something like this. If we wanted to save data that's coming in on channel 2, when we have this marked for saving, then we would place a check in this box. If you wanted to save a channel that you aren't also displaying, then you can do that. If you wanted to display channels that you don't want to save while you have save enabled, you can do that as well. So bear all this in mind. Also, from the channels window, you can set whether to auto read. This will at the very beginning of an acquisition, while the shutter is closed, it will read the signal and determine the dark current level and subtract it from every sample that's coming in during the acquisition. So we talked about saving a little bit. Let's go into a little more detail. So if you want to save images that you're acquiring in ScanImage, then you would place a check in this save box, and then you can specify a directory by clicking this dir button. And you would want to specify a directory that is on a disk with high write speeds. And then you can just select somewhere to save. I think C is okay. Just kidding, this is actually a common pitfall. So you will likely not have administrator privileges for the C drive, so it would be best not to use the C drive, actually. And you should locate another area on your writing drive, if it is the C drive in your case. So you would perhaps I'll just go to Documents, and we have a TIFFs folder here, and we can just write to this TIFFs folder where we have no issues writing to. And then you can specify a base name specific to the experiment, and then this acquisition number will increment for every time that you save a separate file, and once you start and end an acquisition, that will wrap up a single file and increment this acquisition number. And you can specify a number of frames per file. If you want to limit how big an individual file gets, you can say only 200 frames get logged to any one file, or you can leave it at inf for an infinite number of frames per file. And this number averaged, this is the same as this frame rolling average factor, but this time for the frame data that is going to be logged to disk. You may just leave this at 1 all the time so that you can average in post, and that way you don't lose any temporal resolution of your imaging. So now we can grab, if we wanted to say the number of frames to acquire in our TIFF, we could do so from here. I'm going to disable stack, so we do a planar acquisition. So now we can acquire 5. Let's say we do want to do, I guess 5 frames is good enough. Let's start a grab. Okay, and so now the frame should have come here, and now if we want to view the image data, you can use a program like Fiji, which is just ImageJ. But if you try to use ImageJ, you might run into some issues, so I'd suggest Fiji. And here we have our image data. You can do some image analysis with Fiji if you'd like. If you would like to view the metadata that we store into the file, then you can execute this command, scanimage.util.openTIFF, which has these output arguments. You can also get the image data this way, but important here is the header. So if we specify the file, and we look at our header, you'll see that the ScanImage object, which is the same as this handle to the SI object, maybe with a few objects taken out for space. This contains all of the configuration that you had done for this particular acquisition, and everything inside of this object, which should be helpful to backtrack what you had done for any particular acquisition that you had acquired with ScanImage. And then also some other information. We have frame numbers and a vector, and so the indices for these frame numbers correspond to this, for this first frame, the timestamp was 0 seconds. For frame 4, the timestamp was 1, 2, 3. 4 is 963 milliseconds into the acquisition. This may be helpful. So that's the imaging data that we normally collect in ScanImage. So now let's do a stack acquisition. So there are 3 different ways of planning a stack acquisition. We have uniform, bounded, and arbitrary means of defining planes at which you would want to acquire. With uniform, we take the current sample location or the current depth and you can specify a number of slices. Let's say we'll do 4 slices with 60 microns in between them to make good use of the T-lens range. And now we have the first slice being acquired at the current location, and then 3 additional slices deeper into the sample. Now, you need to be a little careful with this if you're going to maximize use of the micro T-lens range. You'll see if we look at the waveform from this, if we refresh the waveform, so with this we will go past the voltage range. We'll go past the range that we planned, that we configured for the micro T-lens in achieving this. So our range was from minus 250, we started at minus 200, and then we have an upper travel range of 10 microns, and this is either right at or past this 10 microns. So if it hasn't already, yeah, we are seeing that we have a warning in the command window. The fast C waveform exceeded the actuator range, clamped max and min. So from our stack window, we have these 4 slices, and if we were outside of the range, if I had set this to something like minus 100, I would have seen that 2 of these slices definitely went outside of the range. What is not currently displayed in the stack controls, and what we probably should improve on here, is that even so a thing about sawtooth waveforms, when we do a fast C stack with sawtooth waveforms, we're going to travel with the fast C device at a constant velocity. So we're going to acquire 1 frame per slice going at constant velocity through the stack. And so the way it works is we're going to travel 60 microns while acquiring this frame, and then we're going to travel 60 microns while acquiring this frame, 60 microns while acquiring this frame, and guess what? We're also going to travel 60 microns past minus 20 microns and end up at plus 40 microns before we cycle back to this first depth here. And 40 microns is much greater than our 10 micron bound that we have for upper travel range. So just be wary of this when defining your stack. So right now, with our starting position at minus 200, our starting position is 40 micron or 30 microns past the bound. So let's go back at least 30 microns. Let's start from minus 240 microns. So this should give us a proper waveform. And there we go. So that is fine. And then what you might have thought was a little weird here was this shape of the voltage waveform we're sending. So we have a lookup table for the micro T-lens that accounts for the nonlinearity of its relation between the command voltage and the position that it's at. So that is why we have this nonlinear waveform. So that's one of the waveforms. That's the sawtooth waveform. For step waveforms, this is not an issue. We're not going to have a constant velocity change between each slice, and actually we're just going to stop at each location and image. So it will just go straight from this location back to the beginning. Also, a good thing about step waveforms is you are able to use more than one frame per slice, so you can average some frames between slices or between volumes. And the one thing about a sawtooth waveform that is maybe preferable to using a step waveform is the speed. So you can have a higher volume rate, acquiring just one frame per slice, and with a constant velocity of the Z Z actuator. That's easier for the Z actuator normally to handle. I'm not entirely sure how well the micro T-lens performs, but I assume that since it's not having to deal with the mass of an objective, like with an piezo objective stage, that it can handle, may be able to handle step waveforms better. So you may use step waveforms. If you see some artifacts in your imaging from a step waveform, as though maybe on the first frame of every volume there's still it looks like the micro T lens was still moving the focal point during the acquisition of the first frame or first few frames, then you might increase this volume flyback time. So if we give multiple volumes to acquire, we can set this number to a huge number, and that's fine. If we increase our volume flyback time, let's see, for a sawtooth waveform, and our frame rate is 3 Hertz, which is approximately 300 milliseconds per frame, and we could throw away 2 frames, or I guess 3 frames of time between volumes, using this volume flyback time to give it time to reach the position before starting acquisition for the next volume. All right, and so that's mostly what we can say about configuring the fast stack, regardless of how we define the slices. But let's visit bounded slice definition. So if we wanted to, instead of just from the current sample position and some constant step size down, we can do a focus in our sample. Let's bring up our display. So we can focus on our sample, and if we're say we're at the very top of the range that we're looking to image, and we want to image here at the top as well, we can set our start at this position. Say this power that we have is an appropriate amount of power at this C. We can just set this as the top of our stack, and then we can move to the bottom. Say that we may have a lot of range, but we're only interested in scanning from minus 240 to minus 163 microns. I can set an end. Maybe I need a little bit more power at this depth. Maybe 17% is good. So now we've defined our stack, and we've also defined a power versus depth lookup table using a exponential fit using this equation here. We've used the 2 points defined here to define what this characteristic length would be, and we're able to interpolate for these other 2 depths what the power should be. So this would be a good way of defining slices as well. You can define the number of slices here still, or you can define a step size, and that would determine the number of slices you would be acquiring in this stack. And then if you don't want a constant step size between slices, maybe you want one slice that's further away from the other ones, there is arbitrary stacks. So for arbitrary stacks, you can just input the depths in sample coordinates precisely where you would want to image. And you cannot acquire arbitrarily defined z's using the sawtooth waveform. You need to use step, and then that would work. That is another way to specify your z's. So anyway, let's go ahead and acquire with this. Actually, we need to bring this back. Okay, so now we're in range and we can start our grab. And there we go. I mentioned before that we can acquire as many volumes as we want, as long as you have disk space, or as few volumes as you want. You may have defined more volumes than you actually intend to acquire. You can abort, and if we were saving, then it would save all of the data that we had collected up to that point. So that concludes the demo, but here are just a few more things. There are a few features not covered that may be of interest, and it's probably best that you are made aware of them early on. In green here, we have a ScanImage plugin. In black, we have features available in basic ScanImage, and in blue are premium ScanImage features. This isn't an exhaustive list, but just a few features of interest. So first, I'll mention the distortion correction plugin. This needs to be brought into ScanImage source code from the MINI2P toolbox repo. And I'll show you exactly where to find it. So from the toolbox, if we go to software and then MINI2P SI device, you'll find all of the things that need to be brought in, and then this README document right here thoroughly shows how to install it and use it. Beyond that, we have the stage scanner alignment feature, the VDAC test panel for any troubleshooting, the data recorder and the waveform generator can be used to use the VDAC's analog inputs and outputs. You can use user functions to allow you to run your own scripts at certain times within an acquisition. Beyond these basic ScanImage features, ScanImage Premium has auxiliary triggers, which allows you to timestamp events and match them to events to the frame that it occurred on. We also have online analysis and output channels, which allow you to see the fluorescence over time plots for ranges of interest within the collected frames while you're collecting them, and also output signals or execute code based on the live fluorescence traces. You can do this for multiple regions of interest. Also helpful for complex experiments using multiple computers and or multiple MATLAB-based softwares is ScanImage Remote Control, which allows you to control ScanImage from a second MATLAB instance on the same computer or a different computer on the same network. Some other noteworthy features include arbitrary line scanning, photostimulation, multiple regions of interest, photon counting, and low repetition rate laser gating. For more information on any of these, you can read through our documentation at docs.scanimage.org. Other things to note are that the Miracle MEMS cannot be controlled as a resonance scanner from NI hardware in ScanImage with our Miracle device implementation. Another thing, if you want, you can scan this QR code to go straight to our ScanImage documentation, which I just mentioned. And ScanImage is sold with 12 months of support and access to updated releases, after which, for more support and access to updated ScanImage, licenses can be renewed annually at a substantially lower cost. To ask for a quote, you can email us at info@mbfbioscience.com. I hope this presentation was helpful to you, and I wish you the best of luck on future experiments with the MINI2P.